Assalamualaikum warahmatullahi wabarakatuh. We are from Group 5 and our member are Muhammad Haziq Imran, Muhammad Hafizuddin, Muhammad Aidil Shah, and Amir Din Iqbal. And we are going to present about material science, X-ray diffraction.
What is X-ray? X-ray, or much less commonly X radiation, is some kind of penetrating form of high energy electromagnetic radiation. So now we move to the diffraction. What is diffraction? Diffraction is the spreading of wave around obstacles. Diffraction takes place with sound with electromagnetic radiation such as light, X-ray, and gamma rays, and with very small moving particles such as atoms, neutrons, and electrons. We show wave-like properties. We can see how it works in the image. So basically, it works as the efferent of bending of wave around small obstacles and spreading out of wave past small openings. So we can see in the image, wave move from A to B. So when the wave pass through the small opening, the first layer of wave is smaller than the second layer, and the third layer of the wave is bigger than the second layer. So it means that the wave is spreading after it passed through the small opening. Next, we move on to X-ray diffraction. What is the X-ray diffraction? According to the characterization techniques for hybrid nanocomposites based on cellulose nanocrystal and nanoparticles, X-ray diffraction, or we call it XRD, is an analytical technique based on the diffraction of X-ray by matter, especially for crystalline materials. The atomic planes of crystal cause an incident beam of X-rays to interfere with one another as they leave the crystal. The phenomenon is called X-ray diffraction. Next, we move to the application. With specialized techniques, XRD can be used to determine crystal structures using rate field refinement. Second, it can determine the model amounts of minerals. And thirdly, characterize thin film samples. In 1912, Max von Leo came upon the idea that X-ray passing through crystal might create similar patterns. That is, a crystal structure would correspond to the openings in a screen. Experiment confirmed Max von Leo's idea. This demonstrates that X-ray could be described as wave. The method also made it possible to use diffraction patterns to determine crystal structure.
X-ray diffraction, or XRD, is an analytical technique based on the diffraction of X-ray by matter, especially for crystalline materials. X-ray diffraction is an elastic scattering without loss of photon energy, giving rise to increased interference as more ordered material is analyzed. The primary use of XRD analysis is the identification of materials based on their diffraction pattern as well as face identification. XRD also yields information on how the actual structure deviates from the ideal one, owing to the internal stress and defects. X-ray diffraction is based on constructive interference of monochromatic X-ray and crystalline sample. These X-rays are generated by a cathode ray tube filtered to produce monochromatic radiation collimated to, to concentrate and direct toward the sample. The interaction of the incandescent ray with the sample produces constructive interference and a diffract ray when the conditions satisfy Bragg's law. These diffracted X-rays are diffracted, processed, and counted by scanning the sample through a range of two theta angles. All possible diffraction directions of the lattice should be attained due to the random orientation of the powdered material. Conversion of the diffraction peaks to D-spacing allow identification of the mineral because each mineral has set of unique D-spacing. Typically, this is achieved by comparison of D-spacing with a standard reference pattern. Next one is the Bragg's law. The structure of crystal and molecule are often being identified using X-ray diffraction study, which are explained by Bragg's law. The law explains the relationship between an X-ray light shooting into and its reflection off from the crystal surface. This Bragg's law was derived by English physician Sir W. H. Bragg and his son Sir W. L. Bragg in 1913. This law related to the wavelength of electromagnetic radiation, which is referred to lambda, and then to the diffraction angle theta and the lattice spacing d in the crystalline sample. Bragg's law refers to the simple equation 2d sin theta equal to n lambda, which is n is referred to an integer. The path difference between the ray reflected at the atom X and the ray reflected at atom Y can be seen to be 2yx. From the law of science, we can express this distance xy in terms of the lattice distance and X-ray indecent angle. If the path difference is equal to an integer multiple of wavelength, then X-ray A and B, and by extension C, will arrive at atom X in the same phase. Then the scattered radiation will undergo constructive interference, and thus the crystal will appear to have reflected the radiation, the X radiation. If, however, the condition is not satisfied, then destructive interference will occur.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adisha bin Muhammad Shah. ID number 2019274134. And now we're gonna get into the calculation of the spacing. First, we get into the objective. For the objective, by the end of this section, you should understand the concept of planes in crystal. You should also know that planes are identified by the Miller index and their separation D. Next, we'll be able to calculate Miller indices for planes and be able to use the spacing equation for orthogonal crystal, and lastly be able to use Bragg's law. Okay, now we get into the lattice plane and Miller indices. Okay, we will be representing a crystal structure on a grid, which is lattice, which is a 3D array of points, which become the lattice points. We can also imagine dividing the grid into set of planes in different orientation. All the planes in the set are identical. The planes are over here are imaginary, and the perpendicular distance between pairs of adjacent plane is the d-spacing. Okay, so if we need to identify them, first we need to label the planes in order to be able to identify them. Okay, we label here A, B, and C. Find the intercept of A, B, and C, which is 1 over 4, 2 over 3, and 2 and 1 over 2. And then we take the reciprocal and multiply up to integer if necessary, if it is in a fraction. Okay, the general label is HKL, which intersect at A is H, B is K, and C is L. HKL is the Miller index of the plane, which we write in round brackets with no comma. Just like this, HKL. Okay, first, and then we take a look at this. We see this plane. The plane perpendicular to Y and it cuts at infinity, 1 and infinity. Okay, so if it is infinity, maybe it become a 0, it's 1 and 0 plane. Okay, so we take a look at this. This diagonal cuts at 1, 1 and infinity. It is a 1, 1 and 0 because infinity equals 0. And index 0 means that the plane is parallel to the axis. As we can see here, it is parallel to the y-axis. Okay, next we take a look at some examples. By using the same set of axes, draw the planes with the following in the indices. Okay. We see here is 0, 0 and 1. So we can see 0, 0. So it is perpendicular to the x and y. So it is up here and 1. If it is 1, 1 and 1, it touches all axes. So it become a triangle. That's all for me.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Hazi Imran bin Azmi. ID number 2019227584. So previously we have learned, or my friend have discussed about the objective of de-spacing. So for my part, I will be explaining about de-spacing formula. So how are we gonna use this spacing formula and how to calculate? So let's begin. Spacing formula are given by L, which is length, over D squared is equal to HKL, which is the plane, and divided by A squared, B squared, and C squared. Okay, so next. We're gonna see for the special cases for cubic crystal. Special cases of orthogonal, A is equal to B and is equal to C. Okay, so we can summarize the formula given from the spacing formula, which is the ABC is equal to A. Okay, equal to A squared, because B is equal to C. Okay, so for example, the plane represent the HKL. Okay, for example, 0, 1, 1 plane is equal to HKL. So for the H is equal to 0, the K is equal to 1, and L is equal to 1. Okay, so to include the plane is equal to the HKL itself. Next. Okay, so for the example given, okay, a cubic crystal has A is equal to 5.2 A. Okay, calculate the d-spacing of the plane 110. Okay, so just use the formula because it's given A here. So we know that A is equal to B and is equal to C. So we can use the special cases formula. Okay, so just use the plane. Okay, so H is equal to 1, K is equal to 1, and L is equal to 0 from the plane. Okay, insert the value of A, which is 5.2. So bear in mind that A here represents to the 10th power of negative 10. Okay, so 5.2 times 10 to the power negative 10 squared. Okay, squared. And then we got using the formula, D is equal to 3.67 times 10 to the power of negative 10, or 3.67 A. Okay. Okay, so for the conclusion, for all of the parts were given, we can imagine planes with a crystal. Okay? As previously my friend have been discussed this, we can imagine planes with crystal. Each set of plane is uniquely identified by its Miller indices HKL. Okay, we can calculate the separation D for each set of plane. Any sets of plane given, we can calculate the D spacings. Okay, crystal diffraction radiations of similar order of wavelength of the interatomic spacing. Okay, we also module this diffraction by considering the reflection of radiation from planes, which is the Bragg's law. Okay, that's all from my group. Thank you very much for your time for listening. Hope you have a nice day. Thank you.